Good morning, everyone. My name is Aman and I'm the GCSE Chemistry tutor for the MyTutor online school. Today's session will be looking at instrumental analysis and the Earth's atmosphere. So if you were here on Monday, you know we looked at positive and negative ions, so it was quite content heavy on Monday. It will be less so today, and we'll be doing lots of exam questions on that topic to kind of consolidate what we covered. If you haven't met me before, my name is Aman and I study medicine at King's College London. I've done over 150 lessons with MyTutor and I've done all the MyTutor online school sessions. As usual, the session will last for 1 hour, so from 9:45 until 10:45. And if you have any questions at all, please pop them into the chat box or the Q&A function as we're going along. Someone's saying that they weren't here last lesson. The only thing that it will impact is when we do exam questions, you might not be as confident with those, but the video is up on YouTube. So after the session or sometime when you've got some free time, I would recommend watching it because it's quite a key topic. So it's one of the core topics for GCSE Chemistry. Okay, so let's get started. So today's learning objectives are to know the advantages and disadvantages of instrumental methods versus simple chemical tests. So you'll remember that on Monday we looked at simple chemical tests for the positive and negative ions. Today we'll be looking at one of the instrumental methods that we need to know about, and we're going to look at the advantages and disadvantages of those. We need to analyse and interpret a result from flame emission spectroscopy. So that is the instrumental method that we'll be looking at today, and I'll be showing you how to look at that and understand what's going on. We then need to understand the theories behind how the Earth's atmosphere developed. So how the lesson will work is we'll look at these two learning objectives first. We'll then do some exam questions consolidating the topic of chemical analysis. So that will be positive and negative ions, and then also this instrumental flame emission spectroscopy. Then we'll go on to the Earth's atmosphere, so looking at the theories behind how the Earth's atmosphere developed and knowing the composition of the modern atmosphere. So our next topic after the analysis will be looking at the Earth, which we'll be doing for the rest of the week. Okay, so let's get started then. We won't be doing a recap today because I'll be doing exam questions with you in just a few slides, and that will kind of recap what we covered on Monday. So instrumental analysis, as I said, these aren't simple chemical tests. They're things that we do to rely on machines. So on Monday, we looked at things like testing for carbonates, doing flame tests, and these are all simple tests that we can do ourselves. We don't have to be trained for it, whereas instrumental methods rely on machines. So we call those instrumental analysis. We don't call them simple analysis, which is kind of the simple laboratory tests that we've been doing. So there are several different types of instrumental analysis, but as I said, the one that we're going to focus on is flame emission spectroscopy. And that's the one that all the exam boards want you to know. The one that seems to focus on it the most is AQA. So I've seen lots of exam questions for AQA. It's a newer topic for Edexcel and OCR, so there aren't very many exam questions on it, but we'll do two today. So hopefully you can see what they're looking for. So the benefits of instrumental analysis, so rather than those simple lab tests that we covered on Monday, are that they're often quicker. So you'll remember, for example, when we're testing for halides, we tend to need to add dilute nitric acid first to remove any carbonate, and then we need to add the silver halide. So it can be quite a slow process, whereas in the instrumental analysis, we can have lots of samples running quickly, and we can get the results really, really quickly on a computer as well, rather than having to look. And when we're looking and using our own simple laboratory tests, it can be subjective. So often when we're distinguishing, for example, between the halide ions, a sample may look white, whereas someone else might think it looks cream. Whereas when you use a computer, it's very accurate at telling you exactly what the sample has done when we've been testing it. So that's basically what I mean by more accurate. And then finally, it's more sensitive. So they can pick up smaller concentrations. So what that means is that if a sample has a very, very little concentration of a halide, for example, it can pick up that halide. Whereas if we did our classic halide test, as I said, dilute nitric acid followed by silver nitrate, we might not pick up that halide just because our test isn't sensitive enough. So the instrumental analysis can be really, really sensitive. But there are some downfalls of instrumental analysis as well. As I said before, you need specialist training. So often we wouldn't be able to do it ourselves. That's why we have to resort to simple lab tests. But people that are trained to do it can do it. But as I said, it's specialist training, and that training can be costly. As well as that, it takes time to train up. As it says, it's costly, so the machines are costly. Running the analysis is also costly. Often they require a lot of energy, and because they're kind of big machines that have a lot going on, that also makes them costly. And finally, the results that we get from the output of the machine often need to be compared with a data set. So what this means is, if you remember when we looked at purity and we looked at the melting and boiling points of substances and we used those to determine whether a sample is pure or impure, we compared to a data set. So I believe the question that we did on Monday was about phosphorus, and phosphorus having a melting point of 45. And we said that if it melted at 45, we know it's pure. And the reason we know that is because the data book says that a pure sample of phosphorus should melt at 45 degrees. So often when we do instrumental analysis, we get a result, but we have to compare to a data book to be able to tell us what that result means. So the computer doesn't often kind of specifically say, well, this is what it is. You have to compare, and that can obviously take time and also mean that you need a full data set. Any questions on that at all? Someone's asking, is this a reliable source? I'm not sure what you mean. Do you mean is flame emission spectroscopy a reliable source? Okay, so no one's asked me any questions about instrumental analysis. So as I said, the one we need to know about is flame emission spectroscopy, and I'll show you what that looks like in just a second. But first of all, why do we do flame emission spectroscopy? It's about identifying metal ions in a sample and the concentration of those ions. So hopefully you'll remember that we did flame tests on Monday, or we looked at flame tests on Monday, and we watched a video on those. So it's pretty much very similar to flame tests, but it's done in an instrument called the flame emission spectroscopy. And so what that means is that we can look at smaller concentrations of ions. And the main thing is that we can do lots of ions at the same time. So I'll show you that in a second as well. So what do we do when we're doing flame emission spectroscopy? Well, the sample is heated just like it would be in a flame, but specifically they use different heats and different flames, and they cause some of the electrons to jump to a higher energy shell. So you don't need to know specifically what this means, but this is just explaining why we get different colors when we put different ions in flames. So you'll remember on Monday we looked at all the different positive ions, and for example, lithium was red and sodium was yellow. So someone's saying, I missed the last lesson. As I said to the person that said that to me before, that's okay. The first half of this lesson, we're just covering flame emission spectroscopy, and we'll be doing exam questions. So you can have a go at the exam questions, but I would definitely recommend going back over Monday's lesson because it was probably one of the most important ones of this topic of chemical analysis, and we covered quite a lot of content. But the second half of this lesson, we'll be looking at a new topic, so you should be fine. So as I said, we heat the sample in a flame, and what happens is, if you remember that we have electrons in shells, in elements and in ions, and so when we heat it, some of those electrons get lots of energy, and when they get that energy, they can jump to a higher energy shell. But what will eventually happen is that they will lose that energy, and the electrons will fall back into the shell that they were meant to be in. So for example, if we've got 3 electrons in a middle shell, they may move up to the outer shell momentarily while they've got enough energy, and then they'll lose that energy. And when they lose that energy, they'll move back to the middle shell that they were supposed to be in. But what happens when they move back is that the energy is released in the form of light. And it's that light energy that what we see when we do a flame test, and it's that light energy that's picked up in flame emission spectroscopy. And I'll show you that in a second. And so the metal in the sample is identified by comparing the spectrum that's produced with reference spectra. So remember I said one of the downfalls is we have to compare to a database. So we'll see that now. So let's have a look then. So this is typical of what's produced. So these are some of the reference spectra of some of the 5 metals that we might look at. So for example, this is the spectrum for hydrogen, helium, neon, sodium, and mercury. And then you might get a sample like this, which is, for example, the one that we tested. Does anyone want to have a go at telling me which metal that is? So we look at this and we compare this to all these metals and see which one matches. So does anyone want to have a go at telling me which of the 5 metals this one is? Great, yeah, it's mercury. So well done for people that are answering that question. It's mercury. So we compare this sample to the 5 above, and what we can see is that there's 2 purple lines. The only one with 2 purple lines is mercury. So straight away we can see it's mercury, but also all the lines match up. And that is how we tell from our spectrum which one matches up with the reference. Someone's asking, will we do a quiz today? No, there's no quiz today because we'll be doing lots of exam questions. Someone's asking, you know how schools are starting to reopen and some schools are doing online lessons now for schools. Will MyTutor online school continue? Yep, the plan is for it to continue, but the number of lessons will probably decrease. That is not the electromagnetic spectrum, no. So this is just looking at light waves and in different colours. So the graph on the right tells us what the concentration is. So for example, if we have this spectrum of sodium and we want to know, so we know it's sodium, we've done that by detecting, looking at our sample and comparing to the reference spectra, and let's say we've seen that it's sodium. The next thing we need to be able to do is talk about what the concentration of sodium is. So remember I said that with instrumental analysis, that is possible to do. We can look at the concentration. And the way we do that is that the machine will plot this type of graph for you, and it will tell you that using the flame spectroscopy reading or photometer reading, we can look at this graph and determine what the concentration is. So you'll get a little reading with your sodium reference, with your sodium spectrum, and this is showing that if, for example, you get a reading that says a number 4, that means if we look at our graph, we go across and down, and we can see that the concentration of sodium ions would be 0.02. What if we got a photometer reading of 8? What would be the concentration of the sodium ions? So if we got a photometer reading of 8, what would be the concentration of the sodium ions? Great, yep, 0.04. Excellent. So as I said, we go across from the y-axis and then down to the x. So here we'd be on the y-axis and then we go down to the x. So it comes down to 0.4. Yeah, so well done. So we'd have 0.04 grams per decimeter cube. This type of question where you look at the concentration is really, really rare. I've hardly seen any exam questions on it. The most common exam questions I see are comparing a spectrum to reference spectra and determining which ones are the ions. Someone's asking, how do you get 0.04? So I said that there was a flame photometer reading of 8. So you go to 8 on the y-axis, you go across until you reach this red line or this pinky purple line, and then go down until you get 0.04. I did not teach the spectrum last session, no. So this is new content. This is just the final part of chemical analysis, no. So I did not teach the spectrum last session. So someone's asking me, how do you know what the photometer is? So you don't need to know what the photometer is, you need to know what the spectrum looks like that comes out of it, which is what I've just shown you here. So this is what you will get when it goes into the machine and comes out. You will get a reading like this on your computer. Someone's asking, what is the relationship between ions and electrons? Okay, good question. So let's, for example, take oxygen. So oxygen has 8 electrons. It's in group 6 and its atomic number is 8. So if we have oxygen, we know the first outer shell can only have 2 electrons, and the second shell can only have 8. But oxygen has 8 overall, so 2, and it needs 6 in its last shell. So if I draw those for you. So that's our 6 electrons, or the outer electrons in oxygen. When it becomes an ion, remember it wants to fill its outer shell. Oxygen can either lose 6 electrons or gain 2 electrons to fill its outer shell. It's easier for it to gain 2 electrons, and that's why oxygen is a non-metal and it tends to behave like a non-metal, so it will gain electrons. So when it gains those electrons, this becomes the ionic configuration, and it will have a 2 negative charge. The reason it has a 2 negative charge is that it's gained 2 electrons. So the relationship between ions and electrons is that ions will tend to have more or less electrons than the element in its neutral state. So in oxygen, it has more electrons. And then with flame emission spectroscopy, what might happen is that when we heat it, these electrons might move up to the outer shell, and then they'll eventually move back down. And when they move back down, that releases a wavelength of light. Someone's saying, shouldn't it be 2+? No, it should not be 2+. The reason it would not be 2+ is because 2+ means that it is positively charged. It is not positively charged. We've gained 2 electrons, and therefore it's more negatively charged than positively charged. So oxygen is 2-. Someone's asking me, how do you know it's 8? I just remember that oxygen has an atomic number of 8, but you can use the periodic table to tell you that. Tilly has left the session, but you're asking her, when will they start for Key Stage 3, as it's been quite a while since the GCSE ones have been going on. I'm not sure that there are plans to start Key Stage 3, but there are A-level small group sessions going on. So I know A-level started, but I don't think there are plans to start Key Stage 3. I'll check with Tilly for you about that. Okay, so that's everything we need to know about flame emission spectroscopy. So let's do an exam question. So this is a typical exam question. So it says, a sample of water was tested for the metal ions it contained by flame emission spectroscopy. Figure 1 displays reference spectra. So these are the reference spectra of 5 or 6, so 6 metal ions. Figure 2 displays the spectrum for the sample of water. So we've got here a sample of water, and this is the spectrum. And the question is, which 2 metal ions did the sample contain? So this is a typical exam question, and we need to look at the spectrum that we got and compare it to the reference spectra. So any ideas? Which ones did it contain? It has 2 in it. So it says 2 metal ions. So which 2 did it contain? Someone's asking me, how did you know that the photometer is 8? I just said that it could be 8. You'd get a number reading in an exam question, and then you just have to use the graph to tell you when you do the concentration. Okay, so potassium is one of them. Good. So if we have a look at potassium, we can see that that pretty much matches up. Now, if we have a look, potassium has this here, which our sample has. But there's this line here that is not in potassium. Which one has that line that could potentially explain what the second ion is? Great, sodium. Yeah, well done, sodium. So the answer to this exam question would be potassium and sodium. So potassium and sodium. So well done to everyone that gave me that answer. Someone's asking, is the photometer 8 as it is the atomic number 8? No, no, no. So I just gave an example of oxygen having an atomic number of 8. On here, the photometer reading will come out with your reading. So this one didn't produce a reading. So I said if it's 8, just to make sure that people understood how to read the graph. But they'd give you a reading and then you'd use the graph. So you can't work out the reading. You'd have to, it would be given to you. Someone's asking, is that as hard as it gets? Yes, that is as hard as flame emission spectroscopy gets. It gets harder at A-level because you look at it in a bit more detail, but at GCSE, it does not get any harder than that. And I will show you another exam question now. So before we go on to those exam questions, does anyone have any questions on flame emission spectroscopy and the advantages and disadvantages? So we're going to do exam questions covering positive and negative ions and flame emission spectroscopy. Yeah, so for GCSE, it is pretty easy. As someone's just said, it is just about comparing your reference spectra to the sample you get. Okay, let's do some exam questions. So recap, this is our recap then of this Monday, sorry. So alums are salts. They've been used since ancient times in dyeing and medicine and still have many uses today. The alums contain sulfate ions. Describe and give the result of a chemical test to show this. So remember, sulfates are one of the negative ions we learnt the test for last on Monday. What's the test for a sulfate ion and what would we expect to see? So this is a recap. What was the test for a sulfate ion and what would we expect to see? Yeah, I did teach this last lesson. So if you don't know the answer to this, that would probably be why. Okay, so someone is saying flame test. Remember, negative ions cannot be tested using the flame test. You have to use positive ions only for flame tests. Good, so barium chloride. Okay, if we add barium chloride, that is correct. What do we need to add first? So barium chloride is pretty much the main test for sulfate ions, but we need to add something before the barium chloride. Does anyone remember? So when we do negative ion tests, we always add something before we add the main compound that we want to add. Great, dilute hydrochloric acid. So well done to the person that said that. So the correct answer for this would be that we add dilute hydrochloric acid followed by barium chloride. Okay, so that's the test. What would be the result? What would be the result when we add barium chloride to the sulfate ions? What would we expect to see? So the result is not just what's formed, it's what we expect to see. So yeah, people are saying dilute hydrochloric acid and barium chloride. That's the right test for a sulfate ion, but what would we expect to see? I think you should be getting emails about the A-level sessions, the small group sessions. When Tilly comes back, we'll ask her. Okay, I'm still waiting for someone to tell me what the result is. What do we see when we get barium chloride reacting with a sulfate ion? Does anyone remember? What happens when we do that test? What do we see? Someone's told me what's produced. So they've said that barium sulfate's produced. Excellent. So what is barium sulfate? What happens? So barium sulfate is produced. That wouldn't get you the mark. You need to say what you would see. Okay, so no one's answering that question. That's fine. So barium sulfate is a white precipitate or a white solid. So we'd expect to see a white precipitate or a white solid. So barium sulfate produced, which is a white solid or a white precipitate, whichever you prefer. So that's the answer to this question here. Well done to everyone that answered that. The reason we add the dilute hydrochloric acid followed by barium chloride is the dilute hydrochloric acid removes carbonate ions. So we can't just test by adding barium chloride. We have to add the dilute hydrochloric acid first to remove carbonate ions. Okay, how do we test for aluminium ions using sodium hydroxide? Does anyone remember? How do we test for aluminium ions using sodium hydroxide? So you'll remember it was AQA that wants you to know about aluminium, as does Edexcel. OCR want you to know about zinc. They don't want you to know about aluminium. So OCR zinc, AQA and Edexcel aluminium. So does anyone remember how do we test for aluminium using sodium hydroxide? Okay, so someone is saying white precipitate. Yep, so aluminium does form a white precipitate with sodium hydroxide. Good. What else happens when we add sodium hydroxide? If we add excess. So do you remember that when we looked at it on Monday, we always added sodium hydroxide to our metal ions, and then they would usually form a white precipitate or a colored precipitate. If a white precipitate was formed, we would then add excess sodium hydroxide. And if we added excess, two things could happen. It could either stay a white precipitate or it could dissolve. Does anyone remember what happens with aluminium? Does it dissolve or does it stay as a white precipitate? I've had two answers so far and you're both correct. Good, it dissolves. So the answer to this question here would be that sodium hydroxide is added, so NaOH added, and a white precipitate is formed. And then excess NaOH is added, and the precipitate dissolves. So that would be your answer there, and that would get you the 2 marks. Okay, great. Any questions about that? Or we'll move on to the next exam question. Okay, let's move on. Okay, what's the test for carbonate ions? What's the test for carbonate ions? Does anyone remember the test for carbonate ions? So there were 3 negative ions that you need to know about: sulfates, carbonates, and halides. We've gone through the test for sulfates just now. I talked about the test for halides earlier when I was talking about flame emission spectroscopy, and that was doing dilute nitric acid followed by silver nitrate solution. The only negative ion we didn't talk about was carbonate. Good, so someone's told me the answer to that. Anyone else want to have a go? What's the test for carbonate ions? So you want the test and the result. Good, yes, so it's adding hydrochloric acid. So we add dilute hydrochloric acid, and what happens when we add dilute hydrochloric acid? We add dilute hydrochloric acid, that's the test. What are we expecting to happen? No precipitate with negative ions, but good answer, no precipitate. What's the test? Good, carbon dioxide is produced. So carbon dioxide is produced in bubbles. So we can say bubbles of CO2 produced, which we can test using lime water. Excellent, well done. Any questions on that? So that's the test for carbonate. So this is a good recap then of what we covered on Monday. So we've gone through the test for carbonates, we've gone through the test of sulfates, and then the test for halides, as I said earlier, is dilute nitric acid followed by silver nitrate solution, and you will get one of 3 colors depending on which halide you're testing. Yep, and the lime water will turn milky. Okay, so a student identified chloride ions using acidified silver nitrate solution. So the acidified just means that nitric acid's been added, followed by silver nitrate. What would you see when you add acidified silver nitrate to a solution of a low sodium salt? So it's got chloride ions in it. What would we expect to see with chloride ions and silver nitrate? What color precipitate? So we form a precipitate. You've got three choices: white, cream, or yellow. What do we form? Good, it's white. Excellent, it's a white precipitate. And remember, the way that I advised remembering that on Monday was that on the periodic table, the halogens go chlorine, bromine, iodine. So if you think about it as a spectrum, chlorine is white, bromine is cream, and iodine is yellow. So just think about it going progressively more yellow as you go down the periodic table. That's what I do to remember it. Great, well done everyone. Okay, so that was the tests for all the negative ions. So this is kind of looking at positive ions now. A flame test can be used to identify calcium ions. What color do calcium ions give in a flame test? Does anyone remember? This is a bit more tricky because we have to remember all the flame test colors, and there are 6 ions that you need to know about. If you were here on Monday, you'll know that I drew a diagram which might be helpful. I know some of you screenshot that diagram. If you weren't here on Monday, you can have a look at that on YouTube. Yep, so it forms like a brick red and orange red. So good answers, well done. So the answer is orange red or brick red. So calcium tends to form an orange red. I also showed a video on Monday, which you can watch on YouTube, that shows all the flame test colors, which might be helpful. I know there were some people that weren't here on Monday. As I said, that's absolutely fine. You can go back and rewatch it afterwards. Yes, you would get the mark for just saying red. Okay, when a flame test was carried out on my baby food, the presence of calcium ions was not seen. A yellow flame was produced. Does anyone remember which ion produces a yellow flame? So only one ion produces the yellow flame. So it's not iodine, so this is only positive ions. So we're looking at metals only. Great, yep, sodium. So sodium is the only positive ion that produces a yellow flame, so we know this must be sodium, and that is a favourite for examiners to ask about, just because the yellow of sodium is quite distinct. So if you see a yellow flame test, it's always sodium in the exam. Great, we won't do this question. We will do this one here though. So this is a typical flame emission spectroscopy question. So figure 3 gives the flame emission spectra of 5 metal ions, which you can see down here, and a mixture of 2 metal ions. This is the mixture. Use the spectra to identify the 2 metal ions in the mixture. So what do we think? Which 2 metal ions make up this mixture? So again, very similar to the exam question we did when I was showing you the slides. What do we think about this one? Yep, so someone's given me the answers. You're right, good, so it's 2 metal ions, so make sure you're saying 2. So a lot of people are picking out calcium. Yep, I agree with you, calcium is definitely one of them. What's the second one? Good, I've had a couple of correct answers. I'll just wait for a few more people to answer. Yeah, great, calcium and sodium. Really, really good, well done. So someone is asking me, is there a specific way to remember the flame tests? So really good question. Unfortunately, I don't have the diagram that I drew from Monday, but if you remember, I drew a diagram for the positive ions, which I think are the hardest to remember because there are so many. So there are 6 flame test colors you need to know, and then there's what happens when we add sodium hydroxide. I think on Monday, I explained it in a lot of detail. We went through all the positive ions and then the 3 negative ions that you need to know about. I would definitely recommend watching that again, or making notes as you're going along and seeing if you can make your own diagram. So I found that what's really, really helpful is to make a diagram when you're doing these ions and looking at that diagram to help you. So I drew a flow chart on Monday, which I think some people said was quite helpful to kind of see all the positive ions on one page. I didn't do one for the negative ions, but you're most welcome to have a go at doing that. So I would recommend doing that. And just looking at Monday's lesson again. So someone's asking me, why is it sodium? So we can see that it's calcium because calcium is the only one that pretty much goes from left to right and matches. But what you can see is if you have a look here and you have a look at R1, there's some missing. So there's quite a lot missing between here and here. And the only one that's got a lot there is sodium. And the other thing we can look at are these two lines. So we can see that those two lines are just there, which is not in calcium. So that's why it's sodium. Great, well done everyone for doing that. We'll do one more exam question. Let's go back to this one. Okay, so this is also a typical exam question where you've got tests going on and then we have to decide what it is. So this is just focusing on metal and non-metal. So if we have a look at A then, it says we get a flame test color of yellow. So this is going to tell us the metal ion. It's saying there's a solution. So when there's a solution, we're looking for the metal and non-metal and we're going to put them together. So the flame test is yellow. So what's the metal ion? Sodium, good. And it says hydrochloric acid is added and carbon dioxide gas is produced. So what's the non-metal ion? Excellent, so someone has given me the answer. So if sodium's the metal ion, when we add hydrochloric acid, carbon dioxide gas is produced. So which negative ion produces carbon dioxide gas? Carbonate, halide, or sulfate? Which one? Does anyone remember? So we did this a couple of questions ago. Which negative ion gives carbon dioxide gas when hydrochloric acid is added? Great, yeah, so carbonate. So the answer then to solution A is sodium carbonate. Sodium because that's the metal, so sodium, and then the non-metal is carbonate. So we put that together to make sodium carbonate, so that would be the solution A. So let's do the same for B. So we get a brick red flame test. So you'll remember we just covered which one forms the brick red flame test. When we add sodium hydroxide, a white precipitate is formed in excess sodium hydroxide solution. So first of all, sodium hydroxide is still with the positive ion. And then when we add silver nitrate, a white precipitate is formed. Good, yep, so lots of people are giving me the answer to that. Excellent, it's calcium carbonate. Really, really well done. Yep, calcium carbonate. And the reason for that is that the flame test is brick red, so that means it has to be a calcium ion. When we add sodium hydroxide, a white precipitate is formed, which is what we would expect. And we also know that calcium does not dissolve in excess sodium hydroxide, so it will stay as a white precipitate. So that all fits with calcium. When we add silver nitrate, we're testing for a halide, and we're told that a white precipitate is produced, and the only halide that produces a white precipitate is chlorine. So yep, it is calcium chloride. So well done to everyone that gave me the answer to that. And then finally, this third one, we just need to know the metal ion. So this is the only positive ion test we haven't covered today yet, and that is sodium hydroxide being added when you get a coloured precipitate. So does anyone remember which one gives us a coloured precipitate that is green? Yeah, iron, great. Specifically which type of iron? Iron 2 or iron 3? So remember that there are two iron ions we need to know about. The next lesson is tomorrow morning at 9:45. If you're talking about chemistry, that is, the next lesson today is at 11. Good, it's iron 2, excellent. So just as a recap for those that weren't here, with positive ions, so you can either do the flame test or you can do the sodium hydroxide test where you add sodium hydroxide. And when you add sodium hydroxide, two things can happen. You can either get a white precipitate or you get a coloured precipitate, and three colours will occur. The first one is blue, and if it's blue, it is copper 2+. If you get a green colour, it is iron, and that's iron 2+. And the final one you need to know about is if you get a brown colour. I've not got a brown colour in my colour palettes, but we'll just assume this orangey colour is brown, and that is Fe3+. So I'll put brown there, just so you remember. So when you add sodium hydroxide, there are the four things that can happen. You can either get a white solid or you get one of these colours, and that's how you tell which ions are there. Great, okay, so that's it for the exam questions on positive and negative ions and on spectroscopy. Hopefully you feel a little bit more confident now. They don't tend to get too tricky. They are just kind of testing your recall. And what I mean by recall is just about you remembering which flame test produces which colour, what happens when we add sodium hydroxide, and what are the tests for the negative ions. So it's just important to remember that. And as I said on Monday, they are really difficult to remember. What worked for me was creating a flowchart for both the positive and negative ions. I showed you my positive ion flowchart on Monday. And as I said, that's up on YouTube, so you can have a look at that and see if that's helpful. If not, creating something like a mind map, flashcards, so a flashcard for maybe all the flame tests, and then a flashcard for what happens with sodium hydroxide may be helpful. There isn't that much there. So when we looked at it on Monday, hopefully you'll remember there are 6 flame test colours. With sodium hydroxide, as I said, you can either produce these 3 or a white solid. And there are 3 ions you need to know about with the white solid, depending on your exam board. And then with the negative ions, there's just 3 ions, 3 negative ions you need to know about: sulfate, carbonate, and halide. So it might seem quite overwhelming at the moment, but it's something that I would just continue looking at. Someone's asking me what's a flowchart. I haven't got time to go into that now. If you go on to Tuesday's session, I drew a flowchart for the positive ions, but essentially you start off with something and you keep going down a chart until you get your end result. So it's kind of like a yes/no chart. Great. Any questions then on chemical analysis or spectroscopy? If not, we'll move on to the Earth's atmosphere, which is the next big topic we're going to be covering for the rest of the week. No? Okay. If you have any questions, please put them into the chat or the Q&A. All right, so, let me go back. Okay, so what we need to know about today specifically is how the atmosphere developed, and that's what we're going to cover. And the thing that I find most easy to do is to look at it in terms of gases. So we'll be looking at it in terms of 5 or 6 gases and how they helped to form the early atmosphere. And then we'll be finishing up by looking at, well, what is the modern atmosphere? So we'll look at the old atmosphere or the early atmosphere. So what happens when the Earth was just formed, and then we'll look at what the atmosphere is like right now. Someone's asking, how do you know the intensity of the spectrum from the diagram? So that's a really good question. So the intensity is pretty much the concentration. So they would give you a number and then you have to use that graph to figure out the concentration of whichever ion is there. So really good question. Okay, so let's start off then with what scientists believe happened 4.6 billion years ago. And this is a key number to remember, 4.6 billion years ago, because that's when scientists believe the Earth was formed. So a lot of scientists believe that volcanoes erupted. And when these volcanoes erupted 4.6 billion years ago, they brought any chemicals and gases from inside the Earth's core, so inside the rock of the Earth, out from the volcano, out into the atmosphere. And when they brought them out into the atmosphere, they brought certain gases with them. And the gases they produced were mostly carbon dioxide, that was the big one that made up the bulk of the atmosphere, water vapor, nitrogen, methane, and ammonia. Now, which gas is missing from there that we know is around a lot right now? Does anyone know? Which gas? What's the main gas that we need to survive? Oxygen. Excellent. So the gas we need to survive is oxygen, because that's how we respire, or how respiration takes place. So what we can see then is 4.6 billion years ago, there was very, very little oxygen. And that is a key point. So the main points from 4.6 billion years ago is that there was lots and lots of CO2, so lots of carbon dioxide, and very, very little oxygen. And the reason for that is that the volcanoes did not bring any oxygen with them when they erupted. So that's the key kind of theory about how the Earth developed. It was about volcanoes erupting and then taking out any of those chemicals and gas from the Earth's core and bringing them into the atmosphere, so into the air. So as I said, we're going to look at this by the gases so that we know, how do we know specifically why there was very little oxygen, why we had water vapor, and then we'll look at the other gases on the next slide. So let's start with oxygen then, because that is one of the most important gases in today's atmosphere. But as I said, there was very little in the old atmosphere or the early atmosphere. How do we know then that there was very little? So we know that volcanoes don't really release oxygen, but that's not enough to tell us that there wasn't much in the early atmosphere. So what we can do, and what many scientists do, is they look at ancient rocks. So they get ancient rocks from the ground and they have a look at them. And one of the main things they've noticed is that these ancient rocks contain iron compounds. And these iron compounds would usually break down if oxygen is present. The fact that they haven't broken down, or the ancient rocks did not break down, tells us that there was very little oxygen in the early atmosphere. So that's one of the main theories for why there was very little oxygen. So this theory here is one of the main ones for why there was very little oxygen. So looking at the ancient rocks, there were iron compounds present, and those iron compounds can only be present if there was very little oxygen in the atmosphere, because otherwise they break down. Someone's asking me, how did oxygen form? We're going to get onto that in just a second. So now we've confirmed that there was probably very little oxygen in the early atmosphere because volcanoes didn't release it, and ancient rocks, so one of the first formed rocks, had very little oxygen. They had lots of iron compounds, which would have broken down if there was oxygen. They didn't break down, so that means there was very little oxygen present. So then, as someone's just asked me, how did we get oxygen on the atmosphere? How are we here today? Well, it's believed that about 3.4 billion years ago, so remember the Earth formed 4.6 billion years ago, but 3.4 billion years ago, there were some simple organisms, and these used the breakdown of chemicals as energy. So chemicals in the atmosphere, chemicals in the rocks, they used those as energy. And when they used those as energy, eventually we started to get bacteria and algae made. And these bacteria and algae, so these things evolved, these simple organisms, when these bacteria and algae formed, which was 2.7 billion years ago, remember photosynthesis takes place, so they are plants. So photosynthesis took place, and they used the carbon dioxide that was abundant in the atmosphere. Abundant means that there was plenty of it. So they used the carbon dioxide that was in the atmosphere to produce oxygen. So how we were formed was that these bacteria and algae, which formed from simple organisms, used carbon dioxide in the atmosphere to undergo photosynthesis. And when they undertook photosynthesis, oxygen was released into the atmosphere. And over time, the levels of oxygen increased from photosynthesis, allowing more plants to grow, because remember they need glucose and oxygen to grow. And as they grew, more oxygen was present, more plants were present. And that's when the first kind of organisms that were like humans started to be produced, and they ate things like plants. So we can't eat things like bacteria and algae, so they couldn't come around until plants were there. Any questions on oxygen then? So it started off 4.6 billion years ago with very little oxygen, and today there's lots of oxygen, which we'll go into the modern atmosphere in just a bit. But any questions on oxygen? Okay, great. So the next gas that we're going to look at then is water vapor. So there are two things that we need to know about water vapor. So as I said, volcanoes did release some water vapor. They mainly released carbon dioxide, so there wasn't much water vapor. So that's why it says mostly here. So they mostly released carbon dioxide, but they did also release a bit of water vapor. And what we know is that when they released that water vapor, it condensed. So what does condensation mean? What happened to the water vapor then if it condensed? So we had water vapor and it condensed. What does condensation mean? Yep, great. So that gas, the water vapor was a gas, it turned into a liquid, it condensed. And the reason it turned into a liquid was because when the volcanoes erupted, the earth was really, really hot. So that's why water vapor came out as a gas, and that's why we had loads of gases. But eventually the volcanoes stopped erupting and the earth cooled down. And when it cooled down, that allowed the water vapor to condense and become a liquid. And what happened was all that water vapor in the air that then condensed fell as rain. It fell as rain and it went into the pits in the Earth's crust. So the Earth was not all smooth. There were pits in it. Remember, we had volcanoes erupting, so there were cracks basically in the Earth. And that rain fell into those cracks. And that's how we got our oceans, by rain falling into the cracks, expanding those cracks and allowing oceans to form. That's how the oceans were formed, so from water vapor. The second theory with water vapor was that we had frozen comets. So comets are made of ice, pretty much, and they're in space. And these comets, which were frozen balls of ice, as I said, they fell onto the Earth and they melted on the Earth's surface. And when they melted, we got more liquid that fell into the pits and helped to form oceans. So the theory of how we got water on the Earth came from water vapor released by volcanoes, and then it condensing, or frozen comets falling to the Earth. And when it condensed, or those frozen comets fell to the Earth, we got water that then went into the pits of the Earth, or the cracks of the Earth, to form the oceans. Okay, any questions on water vapor? So we've looked at oxygen and water vapor so far, and how they helped us to form the Earth as it is today. Okay, so no questions on that. So let's move on to the next 3 or 4 gases. So the next big gas that we need to look at then is carbon dioxide. So we know that carbon dioxide was plentiful in the early atmosphere because most of the volcanoes released lots and lots of carbon dioxide. So that's what it means by this was the most abundant gas. So that's what that means. Someone's asking, how was water formed? I've just explained that. So abundant just means plentiful. There was lots of it. It was the most kind of present gas in the atmosphere. So someone's asking me, how was water formed? As I said, I've just explained that. So it came from water vapor released by the volcanoes that then condensed and fell. So that's how water was formed. Okay, so carbon dioxide. It was the most abundant gas, the most plentiful gas, or the most present gas in the atmosphere. And we've already talked about how it was used up in photosynthesis to form glucose. So remember, photosynthesis takes in carbon dioxide and forms oxygen and glucose. So what we already know is that in the early atmosphere, if there was loads and loads of carbon dioxide, when photosynthesis started taking place, that carbon dioxide began to reduce because it was being used up in photosynthesis. So that's one of the main ways that carbon dioxide was reduced. There are a couple of other ways. The other way is that we know that carbon in the glucose would be transferred to tissues such as skeletons when eaten. So what that means is that animals will tend to eat glucose, so we need that as food. And when they eat that glucose, remember glucose is C6H12O6, so it's got carbon in it. The carbon in that glucose would tend to go into the skeletons and bones of those animals. And when they died, they would decompose and get eaten. And when they got eaten, the carbon would be taken in. So a lot of that carbon would be eaten, or if it's not been eaten, when they die, it would get buried under plenty of rock. And hopefully you remember from a couple of weeks ago that we looked at fossil fuels and the burning of hydrocarbons, and you'll remember that many of the fossil fuels come from carbon. So when these animals died, if they weren't eaten and they were allowed to decompose, then the carbon compounds would get buried under plenty of rock, and that created our fossil fuels. Specifically, the three fossil fuels, coal, crude oil, and natural gas, were produced. So coal was made from plants. So any plants that had taken in any carbon compounds, when they died, they would die in swamps and they would get buried under lots of rock in those swamps. And that would put them under a lot of pressure. They would be without any oxygen when they died, and that allowed coal to form. Crude oil and natural gas, so we looked at crude oil specifically. Hopefully you remember it made from phytoplankton. So again, just like with plants, instead of being buried in swamps, they were buried on the earth, and they were buried under lots of rock, again, lots of pressure without any oxygen, which allowed crude oil and natural gas to form. So one of the other ways that carbon dioxide was used up was when all these plants and phytoplankton died, allowing carbon compounds, specifically fossil fuels, to form. So the first way was in photosynthesis. The second way is pretty much producing fossil fuels. The third way is that carbon dioxide is dissolved in oceans. And what I mean by that is that it went into the oceans, or just the gas went into the oceans and dissolved. And when it dissolved, it reacted with metal oxides in the ocean to form carbonate compounds. So one of the most common compounds is limestone, which is made of calcium carbonate. So that means that the carbon dioxide reacted with calcium oxide in the ocean. So the oceans still had lots of metal oxides in them, and they reacted with carbon dioxide to produce carbonate compounds, one of the main ones being limestone. So the three ways that carbon dioxide was used up from the early atmosphere, because remember it was one of the main gases in the early atmosphere, it's not today, and we'll cover that in just a second, was in photosynthesis. When they died, they became fossil fuels. When those animals died, they became fossil fuels, all plants dying, and then it being dissolved in oceans. Okay, any questions on that? So someone's asking, when the plants take in carbon dioxide, they release oxygen. So that's photosynthesis. That process is known as photosynthesis. So that's exactly the process I'm talking about. Someone's asking, has global warming affected the Earth's atmosphere? It has, and we are looking at global warming tomorrow. So hold off on your questions about global warming. We will be talking about global warming tomorrow. That's all of tomorrow's topic. Okay, so the final gases we need to know about then are methane and ammonia, and then nitrogen. So let's start with both of these, methane and ammonia, and the reason they're in the same box is because it's very similar what happened to them. So these gases were present in trace amounts in the early atmosphere. So you'll remember that I said that volcanoes release methane and ammonia, but again, very little was produced because mostly carbon dioxide was produced. Now, methane and ammonia are both toxic gases, so they aren't around today because they are toxic. And the reason they're not around is that when oxygen started to be produced by photosynthesis, the oxygen reacted with methane and ammonia. Specifically, the methane reacted with oxygen to produce carbon dioxide and water. So the reaction for that is actually just like combustion. So it's pretty much a combustion reaction that took place. So methane reacted with oxygen to produce carbon dioxide and water. Let me just make that, oh no. Okay, hold on. Let's see if I'll just put it over here. And then if we try and balance that equation, it says 1 carbon, 4 hydrogens, 2 hydrogens. So we know we're going to need to make that a 4. Now that's 4 hydrogens, 2 oxygens, but now we've got 4 oxygens, so we need to make that 2. So that's the fully balanced equation for methane becoming carbon dioxide and water when it reacted with oxygen. And then I said that also ammonia reacted with oxygen to produce nitrogen and water. So the equation for that reaction is ammonia, NH3, reacted with oxygen to produce nitrogen, N2 plus water. And then again, if we try and balance that, 1 nitrogen, 2 nitrogens, so we need 2, 6 hydrogens, 2 hydrogens, so we need 3, and then 2 oxygens here, but 3 oxygens here, so that's not balanced. So that means everything is going to need to be doubled up to try and do that. So if we have a look now, because we've got 3 oxygens here and only 2 here, that means if we double everything, so we make this a 4, we make this a 6, then this nitrogen now needs to become 2. We now have 6 oxygens, so we can make that 3. So that's where everything just needs to be doubled, otherwise you end up with fractions. So that's the balanced equation there for ammonia reacting with oxygen. So any questions about methane and ammonia? So they reacted with oxygen produced by photosynthesis. Someone's asking, can you still use methane and ammonia? So methane is still one of the hydrocarbons that's produced via combustion when we crack when we crack crude oil and when we do fractional distillation of crude oil, but it's not in the Earth's atmosphere today because it's toxic. Same with ammonia. Ammonia is quite a toxic gas, and if you've used ammonia in the classroom, you'll know it has quite a strong smell as well. Okay, so the final gas we need to know about is nitrogen. So nitrogen is unreactive, and as we said, it's been produced by reacting with oxygen. So this says here it was built up when ammonia reacted with oxygen, and it was released by volcanoes in the early atmosphere. So if you have a look here, it was released by volcanoes in the early atmosphere. So actually, nitrogen built up over time, and because it was unreactive, it was produced when ammonia reacted with oxygen, so it didn't get used up, it actually got produced. And it was unreactive. So any nitrogen that was in the early atmosphere stayed and actually got built up as ammonia reacted with oxygen. So what we can see happened to most of the gases then is that oxygen over time increased because there was very little oxygen in the early atmosphere, but that increased over time. Water vapor, again, that kind of decreased. And the reason for that was because the water vapor actually condensed and became water itself. Ammonia and methane are not on the periodic table because they are simple molecules. They're not all compounds, they're not elements. Carbon dioxide decreased. Remember the 3 ways: photosynthesis, producing fossil fuels, and it dissolved in oceans. Methane and ammonia decreased, again, because they reacted with oxygen produced by photosynthesis. And then finally, nitrogen actually increased. So the only gases that increased were nitrogen and oxygen. The other gases all decreased. And that's what's helped to form today's atmosphere. So today's atmosphere then is here on our pie chart that I've drawn. So I'll just explain this. So first of all, there is one gas that makes up 78% of the atmosphere, and that is nitrogen. And the reason for that is that we don't really use nitrogen in the atmosphere. So that's just pretty much stayed quite constant at 78%. It increased over time because it's unreactive. Ammonia reacted with oxygen to produce nitrogen, and there was some there in the early atmosphere. So that is the most abundant gas because we don't really use it. So that's nitrogen. Oh, you can't see that. Let me do a different color. So yeah, that's nitrogen. 21% is made up of oxygen, and the reason that that's less than nitrogen is because we obviously use up oxygen. We need it for respiration. So this is oxygen here. So 21% is made up of oxygen. And then we're left, so 78 plus 21 is 99%. So we're left with 1%. And that 1%, 0.9% of that 1%, so that's 9/10 of that 1% is made up of argon. So 0.9% is made up of argon. And then 0.1%, so very, very small percentage, is made up of carbon dioxide and trace gases. Specifically, carbon dioxide is 0.04 and the trace gases are 0.06. So you do need to know the exact compositions. So nitrogen is 78%, oxygen is 21%, argon is 0.9%, CO2 is 0.04%, and the trace gases are 0.06%. So that's the composition of the atmosphere now. Someone is asking, do we need to know the exact numbers? You do, yeah, unfortunately. Again, the way I remembered it was by using a pie chart, drawing out my own pie chart, and just looking at it frequently, and hopefully those numbers will you'll start to remember them. As well as that, in the news they're often mentioned because people do know about these numbers. They've known about them for quite a long time, and specifically carbon dioxide is increasing. So it actually used to be closer to 0.03%. It's now closer to 0.04%. So that is increasing, and we will look at that in more detail tomorrow when we look at global warming and why carbon dioxide is increasing. Argon is not an oil, so there is argon oil, that's different. This argon is specifically one of the noble gases, so no. Argon oil is something different. Any other questions? Yep, the carbon footprint, again, we'll be looking at that tomorrow, so I'm not going to cover that today. Global warming and anything to do with the carbon footprint we will be looking at in lots of detail tomorrow. But any questions on that at all? Okay, so let's do an exam question to finish off then. Okay, so this table shows a comparison of the atmospheres of the Earth and Venus today. So Venus pretty much represents the Earth's old atmosphere. So both Mars and Venus, they represent the Earth's kind of early atmosphere. So that's why they don't have life on them at the moment. They're still representing the Earth's early atmosphere. So in the Earth's atmosphere today, the main gas is what? So you can either look at this table or remember the pie chart that I showed you. Yes, oxygen only goes around as a gas, as a paired molecule, O2. Tilly is back. Yep, so I can ask Tilly for you. Tilly, we've had questions about Key Stage 3. Are they going to be on the online school?
So we don't have plans to introduce Key Stage 3 anytime soon. It's definitely a conversation we're having, but there just hasn't been as much demand for that from people. So no, not currently. Okay.
Great. And the other question we had was about the A-level small group teaching. How do students get involved with that if they want to do it?
Okay, so if you're signed up to the online school via email, which I assume all of you are, then there would have been an email through, I think it was at the end of last week, which had information about the online classes that are group classes. But what I'll do is I'll just post a link to that in the chat here and you can go and have a look. So we have some small group classes in a few different subjects. We've got science, maths, English and history at the moment. So if you want to check those out, I will just pop a link in a moment in the chat for you.
Thanks. Okay, so someone is saying, so in a billion years, they can form the Earth's modern atmosphere. Yep, it's possible that Venus and Mars could do that. We don't know, is the answer though. Okay, yep, so in the Earth's atmosphere today, the main gas is nitrogen. Well done to people that answered that. What was the main gas many years ago? So remember I said this one was the most abundant gas many, many years ago in the early atmosphere, which was good, carbon dioxide. Excellent, well done. So carbon dioxide. Okay, scientists do not know the accurate composition of the Earth's early atmosphere. Why do we think that is? Yeah, it is all theories, but this question is essentially asking, well, why are we having to use theories? Good, yeah, there was no recording. Again, yeah, we weren't there, so there were no humans there back in the Earth's early atmosphere, so we have to rely on theories, we have to rely on looking at rocks. Excellent, yeah, really good answers here. Great. Okay, so we will finish there. We will be doing a quiz tomorrow morning as kind of a recap of today's session. I hope that all made sense, and I find this topic really interesting. So hopefully you all enjoyed that. So tomorrow we'll be looking at global warming and the carbon footprint. If you've got any questions, please put them into the chat box now. If not, I will see you all tomorrow morning where we'll be looking at global warming, as I said. I hope you enjoyed today's session. Have a lovely rest of the day, and I'll see you tomorrow. Take care. Bye.